Thank you for joining us on our presentation about name data networking on a NetFPGA. Here with us we have Team Spartans and Nerf to present what we've been working on over the past semester.
Hi everyone. So let's consider a scenario what will happen when N-man controls the web. This is an exam time scenario. So the deadline is approaching and some of the sincere students have already started working on the project long back. As we come a bit closer to the deadline, the server is still fine, everything runs smoothly. However, now that the deadline is almost there are complaints of application not running smoothly, and due to the increased multiple requests, the server crashes. What should a server do in such a terrible case? Well, here is our own superhero N-man comes into play. Ensures everything can be smooth and faster than ever before. Now a student comes and asks for MyUSC, and since being a newly hired employee, it goes to the server, asks for MyUSC. The server gives him MyUSC. It ensures that while forwarding it to the student, he makes his own copy. Now, a new student comes asking for MyUSC. It simply gives it back to it in no time. And same goes with any other person asking for it. What if multiple people ask for MyUSC at the very same time? No worries, it takes care of all of them by serving on a first come first serve basis. Different requests can be made as well. Things run smoother and faster than ever before. Hence, everyone is happy and Miss Server can take care of many more things than before.
Now that you have seen the general advantages that there are when using a named data networking protocol, we will cover in detail our processor design. The topology of a named data network is the same as for any normal network. That is, there are clients or requesters, routers, and servers. So first, a client node sends a packet out to a router. In IP, this packet specifies the destination node that the packet should be sent to. However, in named data networking, the packet that is sent out does not specify the destination, but rather the specific name of the data that is desired. This packet is called an interest packet. Once the packet enters the router, it is given to one of our two processors as determined by a processor select state machine. This state machine ensures that packets are received and sent out in order and that every processor is utilized efficiently. We are using two cores in parallel so that two packets can be processed at once, which gives our hardware an additional speed up to that achieved from the use of hardware accelerators.
After we get the interest packet in the processor, we extract the name from the packet and send it to the hardware accelerator. The pattern matcher matches the name and gives the address to the memory. We have three memory blocks which are being addressed using the address obtained from the pattern matcher. The first one is data cache. Data cache stores the data received from the server for a particular name. The pending interest table stores the address of the requester and the forwarding information base stores the address of the server. If the data is not present in the cache, then the requester address gets stored in the PIT and we extract the server address based on the forwarding information base, which is then used to modify the interest packet accordingly. If the data is already present, then we don't have to go to the server all again to fetch the data. Since it is the first run, we don't have any data in the data cache, so we take the destination address from the forwarding information base and proceed further.
In any content-based routing approach like NDN, it is important for us to know where the packet has to be routed depending on the payload contents. Just we saw that the forwarding information base gives us the information about where the packet has to be routed. We have to make sure that the packet goes there correctly. We have three threads in our processor design to make this happen. The thread 0 is used to change the destination port address, and thread 1 is used to change the IP address, and thread 2 is used to change the MAC addresses. Once we make sure that we change all these addresses, it is important to recalculate the checksum. Once we recalculate the checksum, the packet goes out of the processor. Now we zoom out into the top level schematic where you get the select signal from the state machine that selects which core will be sending this packet out. Once that selects this out, the packet goes out of the output FIFO into the output queue, and depending on the port number, it will be forwarded to the destination.
So let's zoom out the router. and once the router finishes processing the interest packet, it will forward it to the server, and the server will generate the data packet and send it to the router, and the router will duplicate the packet and store it in the data cache, and then send it back to the requester.
Now that you've seen one scenario for our named data networking protocol, let's look at a different one. This next scenario will highlight some of the benefits named data networking has over traditional protocols. This time, we send the same interest packet as we had previously. The packet leaves the sender and enters our NDN router. When it gets to our hardware accelerated pattern matcher, this name turns into an address which is used to search the data cache, pending interest table, and forwarding information base. Since it's the same interest as the one before, we will get a hit in the data cache. Instead of forwarding this interest to its destination, we simply send the packet we have in the cache back to the sender. So now the response leaves the router and returns back to the requester. Because the packet doesn't have to go all the way back to the server, the response time will be shorter and the network traffic will be reduced. This all helps with the increasing networking demands we are seeing, especially with the growing popularity of on-demand content like Netflix and YouTube.
So let's talk about the schedule. That's what we have done so far. And recently we have done the encryption, decryption, and NDN testing.
Next, we will discuss the setup of our benchmark experiments, both on hardware and software, and compare their performance. So the experiment begins by sending a package labeled A to the server that contains the data A. This server will send the data back to the router. It will get cached and sent to the client. This same data will then get sent to the router, and because it was cached, will be sent back to the requester. We will also send a different data, B, which is held on a different server, which will bypass the router because it isn't cached, and then return, getting cached in the router and sent back to the client.
For our deter setup of the experiment, we'll have the NetFPGA in the middle as the router. One of the other node will be the client, and the rest will be servers. In our software setup, we'll replace the NetFPGA with another node acting as the router.
So let's look at the hardware part. This is our command to run this hardware. And we first load the reference IC and copy to the control node. And it's running. Okay, and then we verify pin to see if the network is good or not. So it's good. So now we download the bit file and run RKD. Yeah, this is our bit file, and this is RKD, and open that location, input all the instructions, and verify pin. So you can see that it's pin, so it's good. So then we execute the instruction. So now we are open 4 windows, and each window is for one node. This window is for node 0, this one is for node 2, this one is for node 1, and this one is for node 3. So we want to see the packets that go to each node. So we run TCP dump at each node. So it's TCP dump. Destination is node 2. So it's listening. So we also run TCP dump at node 3, destination at node 3. And we do -x to see the content of packets which the node has received. So this is TCP dump for the node 1. Okay, so let's try pin nodes. First try pin node 3 -p 41 -c c1 and we pin node 3, so the node 3 should get the data, but we do content-based routing, which is also for data network, named data network, so it actually should go to N1, node 1. So the node 1 get data, and you can also see that the data is encrypted. 41 encrypted to B, and you can also see the latency is 23 milliseconds. Yeah. So now we try it again. So it becomes 11 milliseconds. It is because for the third and fourth time the data has been stored into the NetFPGA. So if the node 1, node 0 requires the same data, and NetFPGA will directly give the data back to the node 0, which is a requester. So so the node 0 don't need to go to the server and get the data, which is 2 times faster. So now we are pinning node 3, also pin node 3, and use another pattern, which is 42, which is the name of the node 2, and node 2 should get data instead of node 3. So you can see that node 2 successfully get the data. So now let's try pin without pattern and see if it works regularly. We pin node 3, because node 3 actually haven't got any data. Yeah, let's try. So when we do pin without pattern, node 3 successfully get the data. And pin node 2, yeah, and pin node 1. Yeah, this one is node 1. So we enter it, and node 1 got the data. And you can see that for the pin without pattern, which is without name, the latency is 22, and you can see that if we pin using pattern 41 for the third and fourth time, yeah, the latency is 11, because the router has already got the data, so it will directly give back the requester, so it will speed up.
Now that we have benchmarked our system based on latency values, we go ahead and talk about throughput. For this, we used bing command, typing as sudo bing node 0 node 1 minus p41 41 is the name of the interest package which we had used earlier. Over here we can observe that our throughput is coming out to be 93.01 Mbps, 44.52 Mbps, 42.667 Mbps, and so on. The average throughput being 44 Mbps approximately.
Okay, so now that we've seen the hardware performance, we'll go into our software setup. The first thing we have to do is install the libraries for NDN. The most important one is NDN CXX. This contains a bunch of experimental C++ libraries and primitives, which for security and implementing interest in data packets. These are important for us to run our application. So we're downloading them right now. Another application that is included in this download for making NDN work in software is called NFD, or Named Forwarding Daemon. This allows us to create TCP overlays between different nodes, which means that we will have our NDN header underneath a TCP header. Ideally, NDN packets would be routed exclusively through content headers, but the current network infrastructure doesn't support this. The application we are using to send packets is called NDN Ping, which we will show after this download completes. NDN Ping generates an NDN packet that can be routed through the NDN protocol.
So now that we have finished installing, let's take a look at an example of running NDN ping. So first, let's look at stopping NFD and restarting it. Let's take a look at the default interface that NFD setups. As you can see, there are no routing path to any of the nodes, as you can see here, and there's no forwarding interest based on the content header. So now, let's ping without any routing path and see what happens. So on one side of the node, we need to run the application NDN ping server. We're using the content header of ABC, so if it does not match that, we won't get a ping. So as you can see, we see timeout because there's no routing path in between these two nodes. So let's stop that and let's create a routing path. So NFDC register allows us to have a TCP tunnel in between, and at the same time routes that particular content header to the respective node. In our case, it's node 3 through port 6363. And let's take a look and see if the routing path and overlay has been generated. As you can see, the address 10.1.2.3 has been established, and we also see that the content header ABC has been routed. Now we see that we're successfully able to ping between the two nodes. So in order to benchmark software for NDN, we're using node 2 as the router and setting a routing path to node 1 with the content header of ABC. And afterwards, we're routing another path from node 2 to node 3 with the content header of DEF. So with these individual paths, the router node will be able to identify which content header is being sent to it, and it'll be able to route it accordingly. So now if we do NF status, we can see that there's a TCP tunnel for both node 1 and node 3, and that they have indicated which content header will be routed where. So now moving on, we need to make sure the client node, which is has a path to the router 2. So here we're typing in NFDC in order to create a path from the client to the router. And now if we check NFD status, we can see that the route has been made along with the content header. So after establishing path for both content ABC and DEF, we are going to ping the servers from the client. So whenever the client receives an encrypted packet from the client, it will send back data to the client. So in our case, we have one single client sending two types of content header to two different servers, and it will receive data from both servers back due to the routing. In our case, we send 25 packets, and we'll find the average for the latency of each. We are getting around 48 milliseconds for the latency of each packet.
As you can see in this graph of our latency comparisons between hardware and software, the results we found were that hardware was 4 times faster than software. This was due primarily to the use of our hardware accelerators. As for throughput, while we were able to find a hardware throughput value through the use of our Bing application, for software there are currently no applications in the NDN libraries that will calculate throughput. So we are using a measurement that we found. The link is noted here for computing throughput based upon the round trip time and packet size of our ping values we measured in the latency benchmark. Our results here showed that the software throughput was 0.51 megabits per second. The result, based upon these values, was that hardware had a 100 times greater throughput than software. In the future, should a named data networking protocol replace IP, we envision a widespread use of hardware accelerators in its implementation. Thank you.